the most important but the most incompletely understood concept in all of science. In part 1a, we discussed the Bottzmann entropy equation. S equals K ln W, and illustrated there the meaning and use of W, the number of microstates, using a couple of simple examples which are concerned with thermal entropy arising due to the energy level distribution of particles of matter. In this part 1b, we continue to use this equation to understand thermal entropy much more thoroughly. The equation S equals K ln W happens to be the most famous equation in a theory called statistical thermodynamic theory. One of the postulates in this theory is that all microstates corresponding to a given macrostate occur with the same equal probability. For example, as discussed in part 1a, 10 microstates constitute the macrostate of n equal to 3 atoms and u equal to 3 quanta. According to the above postulate, each of these 10 microstates has the same probability of occurring as any other. This postulate then implies, as postulated by probability theory, that the probability Pi for the ith distribution is equal to Wi over W, where Wi is the number of microstates for the ith distribution and W is the total number of microstates for all the possible distributions. This is exactly like the scenario where there are 3 possible events for the tossing of 2 quarters simultaneously, namely both coins landing on heads, one coin on heads and the other on tails, and both on tails, with 4 possible expected outcomes, namely both coins landing on heads, the first coin on heads and the second on tails, the first on tails and the second on heads, and lastly both on tails. Therefore, according to probability theory, the probability for the second event, namely one coin landing on heads and the other on tails, is 2 over 4 equal to 0.5, and that for the first and third events, namely both on heads or on tails, is 1 over 4 equal to 0.25 each. Now, whenever we actually toss 2 quarters at the same time, a large enough number of times n, we always observe that the number of times we get one coin landing on heads and the other on tails is close to 0.5 yen, and that of both coins landing on either heads or tails is close to 0.25 yen. As yen becomes larger and larger, the actual values become closer and closer to the above values. This observed numerical pattern points to a rule followed by nature and is stated in statistics as the law of large numbers, whose mathematical statement is: limit as n approaches infinity of ni over n equal to fi equals pi for the ith event, where n is the total number of actual outcomes, ni is the number of outcomes for the ith event, fi is the fraction of the total number of outcomes for the ith event, and pi is the probability of the ith event occurring. That is, let us say that in one experiment we actually toss 2 quarters at the same time, a total of 10,000 times. Let us assume 10,000 is statistically large enough number of times. Then 1/2 of the actual outcomes, namely 5,000, would be one coin landing on heads and the other on tails. 1/4 of the actual outcomes, namely 2,500, would be the other 2 possible events each. Thus, when only one actual outcome is considered, we can talk in terms of only the probability itself of its occurring. We cannot say which of the possible outcomes will be the actual outcome. Interestingly, however, when we consider a statistically large enough number of actual outcomes, we can equate that same probability to the fraction of the total number of actual outcomes for the given event. Similarly, in the case of n equal to 3 atoms and u equal to 3 quanta, since the distribution d1 is associated with 3 microstates out of the total 10, the probability of distribution 1 occurring is 3/10 equal to 0.3, that is 30%. D2 is associated with 6 microstates, and therefore its probability is 6/10 equal to 0.6 or 60%, and that of D3 is just 1/10 equal to 0.1 or 10%. We say that distribution 2, D2, is the most probable distribution, and distribution 3, D3, is the least probable one. In the case of 4 quanta, D2 is the most probable distribution with a probability of 6/15 or 2/5, and the other 3 are equally probable with a probability of 3/15 or 1/5 each. As the number of particles making up the system increases and is in the order of Avogadro's number corresponding to the macroscopic world, the number of possible microstates for each possible distribution astronomically increases. And at the same time, interestingly enough, the number of microstates W and hence the probability P for one particular possible distribution becomes extremely large in comparison with those for any other distribution. This most probable distribution is referred to as the Bottzmann distribution, and we can assume that the system is basically only in this distribution all the time, and hence all the properties of the system are determined simply by this distribution. For example, in the case of U equal to 3 quanta, when n equals 6 times 10 raised to 23, W1 equals 6 times 10 raised to 23, W2 happens to be 4 times 10 raised to 47, and W3 is 4 times 10 raised to 70, making D3 to be exhibited all the time. In the case of 4 quanta, when n equals 6 times 10 raised to 23, W1 equals 6 times 10 raised to 23, W2 4 times 10 raised to 47, W3 also 4 times 10 raised to 47, and W4 2 times 10 raised to 71, making D4 to be exhibited all the time. Realizing the above, Bottzmann derived an equation to calculate the ni's, namely the number of particles at each allowed energy state for a given set of total number of particles n, allowed energies epsilon I per particle, and Kelvin temperature T. While deriving this equation, he imposed two essential constraints on the Ni values. The first is that they must yield the maximum possible value for the number of microstates W and hence for the entropy S, in accordance with the maximum entropy principle of thermodynamic theory, which states that every system in nature tends to possess as maximum an entropy as possible under the given conditions. The second restriction is that the Ni's should yield the total internal energy U of the system in question as given by the equation U equals sigma Ni times epsilon I, since epsilon I is the energy of one particle, and Ni particles will have a total energy of Ni times epsilon I. This Boltzmann distribution equation is Pi equal to Fi equal to Ni over N equals e raised to negative epsilon I over kT all over Z. Here, as mentioned before, Pi is the probability of the ith energy state being occupied by a particle, Fi the fraction of particles in that energy state, which is equal to Ni over N. Epsilon I is the allowed energy of the ith energy state per particle. Z is called the partition function, which is the sum of e raised to negative epsilon I over kT over all allowed energy states. It is a constant at a particular temperature for a given substance. It determines how the total number of particles is partitioned among the various allowed energy states, and hence its name. An algebraic analysis of the above Boltzmann distribution equation clearly shows two general trends. The first is that as the temperature T increases, N0 decreases while the other Ni's increase. And the second is that as the allowed energy epsilon I increases, Ni decreases. The second one deserves an illustration. Let us say you are told that the three numbers 1336, 18 and 98,646 adding to 100,000 correspond to a Boltzmann distribution at a particular temperature, yielding the maximum possible value of W and hence maximum S entropy. Given the above second characteristic of this distribution, you should immediately conclude that the actual distribution must be N0 equals 98,646, the largest number here. N1 equals 1,336, the next lower number, and N2 equals 18, the smallest number. No other possibility such as N0 equals 18, N1 equals 98,646, and N2 equals 1,336, or N0 equals 1,336, N1 equals 18, and N2 equals 98,646, etc., yielding the same values for W and S can be the actuality. The reason why all these different possibilities yield the same value for W as the actual one is that the factorials of all the Ni's get multiplied in the denominator of the equation used to calculate W, and multiplication is commutative, meaning that the order of factors does not matter. Thus, there is no restriction with respect to W as to which particular distribution is considered. So, what is the reason for the ni's to keep decreasing as I increases? That is, y is ni plus 1 always less than ni. Why does any system prefer this particular kind of sequence over all the other possible sequences? It is simply to ensure that the system also obeys the minimum energy principle of thermodynamic theory, in addition to obeying the maximum entropy principle. According to this principle, every system in nature tends to possess as minimum an energy as possible. Given a particular set of numbers for ni's and the corresponding energies epsilon i's for one particle, as mentioned earlier, U equals sigma ni times epsilon I. The only way to minimize U is to keep decreasing the value of ni as epsilon I keeps increasing. In any other way, the total U will be larger than the minimum possible. Therefore, the energy level populations of particles always keep decreasing as the energies keep increasing at any given temperature. Thus, it should be kept in mind that the Boltzmann distribution always obeys both the minimum energy principle and the maximum entropy principle of thermodynamic theory. Incidentally, without digressing into a detailed discussion, both of the above principles are in turn governed by the minimum Helmholtz energy principle, which states that every system in nature always possesses minimum possible Helmholtz energy A at a given temperature T. The equation relating the changes in A, U, and S at a given T is delta A equals delta U minus T delta S. According to this principle, for a process undergone by a system at constant temperature to be spontaneous, delta A should be negative. The actual sign of delta U or delta S is immaterial. Boltzmann distribution equation ensures that delta U is as negative as possible and delta S is as positive as possible. But this is not an essential condition. An important implication of this principle is that the energy of a system does not always have to only decrease. It can increase, but only if the happiness arising due to an increase in entropy more than compensates for the unhappiness due to the increase in energy. Similarly, the entropy of a system does not always have to only increase. It can decrease, but only if the happiness arising due to a decrease in energy more than compensates for the unhappiness due to the decrease in entropy. The best scenario, of course, corresponds to a decrease in energy and at the same time an increase in entropy. This is the reason for the use of the term tends to in the statements of both the minimum energy and maximum entropy principles. Let us now see in some detail how Boltzmann distribution calculations can elegantly illustrate the second law of thermo, which states that the entropy of an isolated system always increases during a spontaneous process taking place inside that system and thereby shed some light on the working of the second law. An isolated system, by definition, has no interactions at all with the surroundings. That is, no transfer of matter or energy as heat or work takes place between an isolated system and its surroundings. Therefore, when the second law is applied to this system, delta S total is replaced with delta S isolated system. In other words, a process can ever be spontaneous inside an isolated system only if its entropy increases, since its energy stays constant. And after the entropy reaches its maximum possible value under the given conditions, and hence the equilibrium state is reached, delta S equals 0, meaning S does not change any longer. Thus, the second law in this case is stated as delta S isolated system is greater than or equal to 0. We will consider two examples for this purpose. To make the math involved in these calculations doable and much simpler, we will use tiny samples of metals and real low temperatures. First, consider a heat insulated isolated system in which there are two lead blocks, each with 100,000 lead atoms. One is at 50 Kelvin and the other at 150 Kelvin. Both are brought in contact and they automatically equilibrate thermally until the temperature reaches 100 Kelvin. Since both blocks are of the same substance and the same mass, the equilibrium temperature is right in the middle of the two initial temperatures. We can calculate Boltzmann distributions at these three temperatures, namely 50 Kelvin, 150 Kelvin, and 100 Kelvin, using the Boltzmann distribution equation. Let us recall from part 1a of this video series that the allowed vibrational energy levels epsilon V or V plus 1/2 times h nu with V equal to 0, 1, 2, 3, etc. To make the calculations simpler, it is customary to assume, as mentioned in part 1a, that the lowest allowed energy is 0 instead of 1/2 h nu. To avoid dealing with 10 raised to negative 19 or 10 raised to negative 20 kind of numbers, and to have reasonable numbers for the energies, we will use zeptojoule unit, where zepto stands for 1 times 10 raised to negative 21. And the vibrational frequency of each lead atom in the metal happens to be 1.83 times 10 raised to 12 per second. The partition function Z values for the Einstein lead solid at 50, 150 and 100 Kelvin are respectively 1.209, 2.257 and 1.711. Einstein solid is one in which, by definition, each particle executes simple harmonic motion, namely vibrational motion that obeys Hooke's law, which states that the restoring force is proportional to the displacement, and the allowed energy levels are like a uniform ladder with equal spacing. The results are shown in table 1. Notice, as mentioned earlier, that as the temperature increases, N0 decreases and the other Ni's increase. Also, notice, as mentioned earlier, that at each of the temperatures, the populations keep on decreasing as we go to higher and higher energy states. Using the Ni's in table 1, we can calculate the W's at the three temperatures. Using the equation, W equals N factorial divided by N0 factorial times N1 factorial times N2 factorial, etc. and the corresponding S's using S equals K ln W. Since Excel can calculate only up to 170 factorial, and since one has to calculate very large factorials such as 100,000 factorial, 82,736 factorial, 58,450 factorial, etc., one needs to use a very powerful application such as Mathematica. The results are shown in table 2. It can be seen that as the temperature increases, the W value increases also. Without digressing here, we will discuss the reason for this always observed trend after we illustrate the second law. Therefore, the entropy S calculated using S equals K, L and W also increases. And the W values can be seen to be astronomically large. Notice that we are using only real tiny samples and real low temperatures for these calculations. Imagine what the W values would be like in the case of the macroscopic world, where the number of particles is much larger, like Avogadro's number, and temperatures are much higher, like the room temperature. However, the entropies calculated in our example are reasonable values due to the nature of the logarithm operation, whether common or natural. That is, the common logarithm of 1000 is just 3, and that of 1 million is just 6. Thus, the logarithm operation always reduces the original value to a much smaller one. Knowing these W's, calculate W initial and W final for the isolated system consisting of the two lead blocks. W initial is actually the product of W's for 50 Kelvin and 150 Kelvin, not the sum. Why? To illustrate this, let us assume that there are 3 possible microstates at the lower temperature and 5 possible microstates at the higher temperature when we consider each individually, that is, separately. Now, we consider them together to make up an isolated system. In this case, when the former exists in any one of the 3 microstates at any one instant, at the same instant, the latter can exist in any one of the 5 microstates. In other words, for every one of the 3 of the former, there would be 5 of the latter. Therefore, the total possible would be 5 plus 5 plus 5 equal to 3 times 5 equal to 15, not 5 plus 3 equal to 8. And entropy is an extensive property for which we need to invoke addition. These two situations together become a reason why S is taken as proportional to L and W instead of just W, since the logarithm of a product is the sum of the logarithms of the individual factors. Now, one might wonder why we added the number of microstates for the three possible distributions for the solid with n equal to 3 and u equal to 3h nu. Notice that at any one instant, the three particles of that one solid can exist only in one of the microstates of D1 or D2 or D3, not in those of D1, D2 and D3 at the same time. According to probability theory, the OR operator always implies addition of the individual numbers of possibilities to get the total. On the contrary, in the case of two solids at low T and high T taken together, the particles of low T solid can exist in one of their own possible microstates, and at the same instant those of high T solid can exist in any one of their own possible microstates. It is not D low T or D high T, but D low T and D high T. The distinction is with respect to OR in one case, whereas AND in the other. According to probability theory, the OR operator implies addition of the individual numbers of possibilities to get the total. The AND operator implies multiplication of the individual numbers of possibilities to get the total. By plugging the W values in the equation S equals K ln W, we can now calculate S initial, S final, and then S total, which is the same as S isolated system. It is immediately seen that delta S for the isolated system, consisting of the two lead blocks in a heat insulated container, is positive, namely greater than 0 for this spontaneous process of heat flow from the hot block to the cold block. This is the first part of the second law given by Clausius in 1865. And when the above calculations are repeated for temperatures near 100 Kelvin on either side, it is seen that S at 100 Kelvin is the maximum value, pointing to the operation of the maximum entropy principle in nature, and 100 Kelvin is the equilibrium temperature. There is no change in S isolated system after that, and delta S isolated system is 0, which is the second part of the mathematical statement of the second law. We can repeat the Bottzmann distribution calculations for two silver blocks instead of two lead blocks, each containing 100,000 silver atoms, one at 50 Kelvin and the other at 150 Kelvin in a heat insulated container, which when brought into contact spontaneously equilibrate thermally to 100 Kelvin. The frequency of vibration of each silver atom in the metal is 4.48 times 10 raised to 12 per second, resulting in a larger value for h nu equal to 1 quantum of vibrational energy for silver compared to lead, and hence a larger energy level gap. The partition function Z values for the Einstein silver solid at 50, 150 and 100 Kelvin respectively are 1.014, 1.313 and 1.132. The results obtained are shown in table 3. When we contrast the results in table 3 for silver with those in table 1 for lead, a third feature becomes evident. This is also observed in all similar situations and therefore considered the third fundamental characteristic of Bottzmann distributions. We will discuss this also as well as its reason after illustrating the second law. Using these NIs, we again calculate the W's and then S's. If we contrast the W and S values in tables 2 and 4 for lead and silver, respectively, an important consequence of the third feature of Bottzmann distribution becomes evident. We will look at this also later. Next, we calculate W initial and W final as we did before for lead, correctly applying the math seen there, namely W values at 50 Kelvin and 150 Kelvin should be multiplied and not added to get W initial, and W at 100 Kelvin for one block is also multiplied with that for the other block to get W final. We then calculate S initial and S final by adding the individual S's together. It is again seen that delta S total or delta S isolated system is positive, namely greater than 0 for this spontaneous process. When we repeat these calculations for temperatures near 100 Kelvin on either side, it is again seen that W at 100 Kelvin is the maximum value and hence the corresponding S is the maximum, making it the equilibrium temperature. Both examples elegantly illustrate the idea that the W value at the intermediate equilibrium temperature for both bodies in contact is always greater than the total effect on W initial of the individual W value for the body at the lower cold temperature and that at the higher hot temperature. Therefore, the entropy of the isolated system at the equilibrium temperature is always greater than its initial entropy. This is always found to be the case in all similar calculations, and this illustrates the working in nature of the second law of thermo, for which there is no known exception yet. In part 1c, we will discuss the reasons for the fundamental characteristics of the Boltzmann distributions. We will also look at two other simple interpretations of entropy. The first one being disorder of particles, already discussed in part 1a, and in addition how they are wrongly made even simpler.